Hi, this is Mrs. Crane, and in this orbital diagram video, we are going to learn how to draw something called an orbital diagram, which shows the specific location of electrons in an atom. So you may remember the Bohr diagram that we learned to draw already in class. And in this Bohr diagram, the first orbital contained 2 electrons maximum. The second orbital or shell around the nucleus contained up to 8 electrons. And the third orbital contained up to 18 electrons. In this example that I'm showing here of sodium, there's only 1 electron in that third orbital or shell around the nucleus, but it could hold up to 18. So it turns out that these diagrams really aren't very specific at all about the location of the electrons. So imagine for me that your parents come to pick you up from school one day and they go to the office and they ask the receptionist where you are. And she says, "Work is on the 2nd floor." What are your parents going to do? Knock on every door on the 2nd floor until they find you? Of course not. They're going to ask the receptionist what room you're in on the 2nd floor, right? So Bohr diagrams just tell us the orbital, or sometimes we call it the shell, that an electron is in. Is it in the first orbital, second, third, etc.? And that's kind of like the receptionist telling your parents what floor you're on. It's a start, but it's not very specific. So now what we're going to learn about in this video is something called an orbital diagram, which is kind of like a specific address for the location of an electron. Orbital diagrams not only tell us the orbital, 1, 2, 3, so on and so forth, but also the suborbital, which is a more specific space within that first, second, third, so on and so forth orbital. And instead of using numbers for the orbitals, we use letters, S, P, D, and F. And that suborbital is about as specific as your parents, as the receptionist telling your parents what classroom you are in. So the numbers of the orbital, the 1, 2, 3, so on and so forth, you probably already remember, tell us the distance that the electron is from the nucleus, right? So that first orbital is the closest to the nucleus. The third orbital is much further from the nucleus. And those letters of the suborbitals, S, P, D, and F, actually tell us the shape of the space where the electron is within the orbital. So an S suborbital means that regardless of what orbital it's in, 1, 2, 3, so on and so forth, that S orbital is always going to be a sphere. And the P suborbitals are always shaped sort of like dumbbells or figure 8s. And you'll notice in the drawings, the diagram below, that there are 3 possible directions then, right? So the dumbbell could be going up and down. It could be going back and forth, side to side, or it could be coming in and out of the page. So we call those different directions PX, PY, and PZ. And you don't need to worry a lot about that, except later you're going to notice that we always draw 3 p orbitals at a time, and that's why it's just the direction. The d suborbitals are kind of shaped like 4 balloons stuck together, if you can imagine that. And so there are 5 different directions they can go in. And we really won't get much into these, but that's why we always draw 5 d orbitals, suborbitals at a time. And then the F suborbitals are a complicated shape. And that's really all that you need to know, is just that they're there, they exist, they're complicated, and we won't really go there in this class. So our Bohr diagram just got more specific. We can add to what we knew at the beginning of this video. So we have our first orbital, that first shell around the nucleus, and within that first orbital there's a sphere shape, s orbital, and that can hold up to 2 electrons. And that second orbital, remember we said it could hold a total of 8 electrons? Well, here's where those 8 electrons come from. They come from an S, or sphere-shaped suborbital, that can hold 2 electrons, and then a p suborbital that can hold up to 6 electrons, 2 in each of the directions that it can face. And so that 2 electrons in the s suborbital and the 6 electrons in the p suborbital is how we add up to the 8 total electrons that can be in that second orbital. And the third orbital, get these little boxes out of the way. The third orbital contains an s suborbital that can hold 2 electrons, a p suborbital with a total of 6 electrons, and a d suborbital with a total of 10 electrons. And so sure enough, if you add the 2 plus the 6 plus the 10, you get a total of 18 electrons, and that's why that third orbital, as we already learned, can hold up to 8 electrons. So at this point, it's a little bit hard to represent all of these suborbitals in a Bohr diagram. And so now we need to learn to draw an orbital diagram to represent them. So we are going to use arrows to represent electrons. And we are going to put the arrows in these various boxes that are labeled in order of energy. 1s, meaning first orbital, S-shaped suborbital. 2s, meaning second orbital, S-shaped suborbital. 2p, meaning second orbital still, but now the p-shaped suborbital. And notice that there are 3 boxes there because that p shape is a dumbbell, and so it can be directed vertically up and down, horizontally back and forth, or sort of in and out of the board in direction, and so on and so forth. It keeps going. Now, I said that we are going to be putting arrows into these different boxes on the diagram to represent electrons, but there are 3 rules when we place the arrows which represent electrons. 1, electrons fill from the bottom up, so we always start off putting our electrons in the 1s space. The second rule is there's a maximum of 2 electrons that you can put in each suborbital. So each one of those little square boxes can only have a maximum of 2 electrons. And you don't really need to worry much about this because this is really quantum mechanics here, but the 2 electrons that are in the same little space, they spin in opposite directions. Kind of like when you put 2 magnets together, how the north end of the magnet and the south end of the magnet attract. So you have to turn the magnets in opposite directions. If that's confusing, don't worry about it. Just know that that's why when we draw the arrows, we always draw one pointing up and one pointing down. It's because of quantum mechanics, which is beyond what we expect you to remember for this course. And then the last rule, electrons are going to fill the suborbitals of the same level before pairing up. So this takes a little bit of thinking, but I've given you an example where I have placed an electron in each of the p orbitals, px, py, and pz, facing up, and then only after I have one arrow or one electron in each of those spaces have I put a downward facing arrow back at the beginning in the px box. That is the correct way to put 4 electrons or arrows into the 3p orbitals. What is incorrect is the example to the right of the big knot, which is where I crammed the electrons or arrows together a little bit more. Right, so I put 2 electrons in px, 2 electrons in py, and nothing in pz. Think of it this way, if electrons were humans, they'd be humans who didn't like to be crammed close together if they could help it. All right, so let's go ahead and try writing an arrow orbital diagram for carbon. You can see that from carbon's symbol on the periodic table, its atomic number is 6, meaning it has 6 protons. And because for these we assume we have a neutral atom, that means we also have 6 electrons. So we are going to represent those 6 electrons with arrows. Following the 3 rules, we'll start off in our lowest energy orbital, our first orbital, 1s, and I will put 2 arrows into that orbital. And I'll move up a higher energy level, 3, 4, and then let's watch how I place my last 2, moving up into the 2p orbital, 5 and 6. It would be incorrect to put both of them into this orbital here, because if they can, while staying at the same energy level, which all 3 of these are, the electrons would rather spread out. So that now is our our arrow orbital diagram for carbon with all 6 electrons placed. Next we'll try fluorine. According to the periodic table, fluorine has an atomic number of 9, meaning it has 9 protons. And if we assume that this is neutral, which we should, that means also 9 electrons. So if we make our arrow orbital diagram, we will have 9 arrows total. Again, starting by placing electrons in the lowest energy, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And again, you don't have a choice in how you place these last arrows here in the 2p orbitals. They need to be spread out as much as possible first, and only then do you go back and overlap. So there are our 9 arrows for fluorine. Next we'll try phosphorus. Phosphorus has 15 protons and therefore also 15 electrons, which is what we'll be placing in the diagram. Again, starting from the bottom, you notice the pattern hopefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then moving up, 11, 12, 13, 14, and 15. And again, it would be incorrect if I had placed the arrows doubled up in the 3p orbitals. They need to be spread out as they are according to one of our rules for arrow placement. All right, and last one here is bromine. It has 35 protons and therefore 35 electrons. So this is going to be a big one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, now be very careful here. The next lowest energy, right? Because you notice that we're putting these in order of increasing energy as we go up here, right? So our next lowest energy is actually going to be 4s here. Okay, so this is where our numbering gets a little out of order, but just go with it. This will make hopefully more sense soon. So this would be 19, 20, and then spread these out, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. Wow, that's a big one. So please make sure you keep in mind that if you're writing a big enough diagram to get up to 3p, then the next one needs to be 4s. Then you go back to 3d and then 4p, because we are not placing these arrows from left to right on the table, but from bottom to top. So that is all, and we will practice more when we get back to class.